Okay.
Okay.
So, hello everyone.
Okay, sorry, I'll just introduce you. It's a pleasure to have Soutim Das and followed by Soham, and they will talk about the Lovász Local Lemma. Okay, over to you.
Thank you, sir, for introducing me. Today, Soham and I are going to talk about a very fundamental and powerful result of probability theory, which is called the Lovász Local Lemma. And we will discuss some of its far-reaching consequences in the fields of combinatorics, graph theory, and as well as computer science. So, Lovász Local Lemma belongs to a class of methods which are called probabilistic methods. So, this probability, I think all of us have heard about Paul Erdős. So he's considered the father of probabilistic methods. So here is a motivating example from graph theory where we can use probabilistic methods. So suppose we have a graph G with vertex set V and edge set E. Then we can say that the graph surely contains a bipartite subgraph with at least the cardinality of the edge set by 2 edges. So if the cardinality of the edge set is say M, then the graph will surely contain a bipartite subgraph with at least M by 2 edges.
Sorry, are you mean induced subgraph?
Yeah, so by subgraph, I mean a subset of the edge set. So okay. Suppose we have K4. Then, so M is essentially 6 here. So this theorem says that there will be a bipartite subgraph with greater than or equal to 3 edges. So essentially what I'll do is I'll consider just this. So the induced edges. I mean, in this case, this is one partite set and this is the other partite set.
Right.
Right?
Oh,
so
upset of edges.
All right. Okay. So how do we proceed with such a problem? So here is the key idea of probabilistic methods. So in probabilistic methods, what we essentially try to do is we try to prove the existence or the non-existence of some object from which belongs to, some object satisfying a given property among a finite collection of objects. So what we essentially try to do is we use the idea that if we randomly select an object from that finite collection, then there will be a positive probability if an object with a given mathematical property exists in that finite collection, and if we randomly choose objects from that finite collection, then there is a positive probability that a randomly chosen object will satisfy that probability, that property that we are talking about. So essentially, in this problem, how do we use this idea? So the key idea is to introduce randomness. Okay. So, sorry. So, is there any question, sir? Oh, I guess not. So let us proceed. So, okay. So observe one thing. So essentially, if we do a proper red-blue coloring of this, suppose we are coloring all non-adjacent vertices with, say, I'm sorry. So let me write this down. It will become more clear. So consider a red-blue coloring of the vertices. Okay. So to introduce randomness in this problem, suppose you are coloring the vertices uniformly at random with probability half. I mean, red with probability half and blue with probability half. Okay. So now consider the edges. Let E denote the set of edges which have red which essentially look like this. For saving time, I'll write in this manner: red here and blue here. Okay, so this is some other color. Okay, so if we consider such edges, then essentially set of such edges, then the vertices belonging, the vertices that are colored red, that will form one partite set, and the vertices that are colored blue will form another partite set. Okay, so what is the idea? So for every such vertex coloring, we'll have essentially we considered the set of colorings, all possible colorings of the vertices to be a sample space. For each point in the sample space, we will evaluate. So this will be this is a function of points in the sample space. So if we evaluate at this and then we count the number of edges, then what this question asks is that whether there exists some omega in the sample space such that this cardinality is greater than equal to. This is what we want. So if we are able to show that, so this is a very interesting probabilistic method that it's a very basic result. So all of us know it. If we are able to show that this is precisely this, then probability this greater than equal to will be strictly greater than 0. Okay, so we'll be able to prove the existence of such an omega in the sample space. Fine. So what is the probability? So let me add a page here to finish it. Just a second. Okay, I'll finish up the proof on the top of the page. So we can essentially write this down, the cardinality of this down, as a sum of indicators, right? So indicator, I'll sum up over the entire edge set. Indicator, whether this edge belongs to this or not. Okay. Now observe that an edge belongs to this E if and only if it is colored red on one end and blue on one end. So out of 4 possible colorings, we will have, we will consider either the red blue or the blue red part. So that has probability, and since the coloring is done independently, so that will have probability half. So if we sum this up, so if we take the expectation of this, so that is essentially nothing but probability that this edge belongs to E, which is half, and we are summing up over the entire edge set. So this is just fine. So we will find such a red blue, we'll be able to find such a red blue coloring of the vertices such that this subgraph, this bipartite subgraph that is generated by that coloring has at least m by 2 edges, where m is the cardinality of the edge set. So that is the key idea behind probabilistic method, and this is one of the simplest probabilistic method, that if a random variable has expectation a, then probability x greater than equal to a is strictly greater than 0. Okay, so here is another example. This is the first, possibly the first known use of probabilistic method. Okay, so it was shown by Zell in 1943 regarding Hamiltonian paths in tournaments. So it was so note the key point here, that whatever proof I've given you is existential. I have not explicitly given you an omega from the sample space, or I have not constructed that subgraph for you anywhere. I've just shown its existence. So these methods are existential by nature. Okay, so this is a result that there exists a tournament on n vertices with at least n factorial by 2 power n minus 1 Hamiltonian paths. Okay, so I'll not go into the proof again. It will take a lot of time. The approach is very similar. In this, we essentially consider a fixed permutation of the vertices. So that will, if we fill up edges in either direction between the vertices, that will induce a Hamiltonian path in the graph, right? So there are if we are constructing a tournament from scratch, suppose we have n vertices and we want to construct a tournament from scratch. Suppose we fill in, so to introduce randomness, we fill in directed edge between the two vertices with probability half. Okay, so for a fixed permutation of the n vertices, so there is exactly a chance of 1 by 2 power n minus 1, because there are n minus 1 edges and each is being directed with probability half. So there is exactly a chance of 1 by 2 power n minus 1 that permutation, that fixed permutation induces a Hamiltonian path. And if we sum up over all possible permutations, that will give us the total number of Hamiltonian paths, and that will be nothing but n factorial by 2 power n minus 1. So we'll essentially assign an indicator random variable and we'll take the sum of that indicator over all possible permutations. That will give the expected value of that count random variable that counts the number of Hamiltonian paths in a random tournament. So that expected value will turn out to be n factorial by 2 power n minus 1. So there is an assignment or of the directed edges for which we will have at least n factorial by 2 power n minus 1 Hamiltonian paths. Fine. So okay. So here is one more example that for people who are familiar with Ramsey theory. So this is a problem of providing lower bounds to Rk, k in Ramsey theory. Okay. So here's a beautiful result due to Paul Erdos that if such a thing holds, then Rk, k is strictly greater than n. Okay, so Rk, k is the smallest value of, so suppose Rk, k greater than n means if you have a complete graph on n vertices, then if you consider a red-blue edge coloring of the graph, then you won't be able to find, Rkk is greater than n, which means that there exists a two coloring, red-blue coloring of the edges of the complete graph without a monochromatic complete graph of size k. Okay, so such a bound was shown by Paul Erdos. It's again a similar, very similar probabilistic method. So you fix a subset of size k and you check whether it induces a complete graph or not. So if it induces a complete graph, so what you're doing, you are doing a uniform at random edge coloring of kn, right? So what is the probability that a fixed subset of size k induces kk? That is just in the denominator you will have 2 power k many ways, and on the numerator you will have just 2 ways. So if all the edges are colored red or all the edges are colored blue. Okay, so 2 by 2 power k, that gives you, 2 by 2 power k choose 2. You need to have a complete graph, right? So essentially if ei, sorry, let me write down, if ei denotes the event that the ith kk is monochromatic. Okay, then probability of ei is nothing but 2 by 2 power k choose 2. And then if you consider these indicator random variables and sum up over that, that will give you the number of monochromatic kk's. Okay, so this expected value of this turns out to be precisely this quantity. So if the expected value of number of monochromatic kk's is less than, if the expected value is less than 1, then there exists an assignment of the coloring for which there does not exist any monochromatic kk in the graph. Okay, so again, so by introducing a little modification in our probabilistic argument, we get the following bound on Rk, k, which is called the alteration method. So I'll not go into details of this. It will take up a lot of our time. The crucial observation is that in this expression, if we find the largest value of n satisfying this inequality, then that turns out to be something like this. Okay, so upon optimizing n, we can conclude that the value of Rk, K is this, right? All right. So, however, this alteration method argument that improves this bound given by Paul Erdős way back in 1947 by a factor of √2. Okay. So we see that, I mean, there are advances in this field. I mean, we have moved beyond just expectation and first moment methods and so on. And what is interesting about this, that the best possible bound that is known till date on Rk, K is given by the method, the probabilistic method that I'm going to talk about today, which is the Lovász Local Lemma. Okay, so we will come back to this problem once we have learned about Lovász Local Lemma, and then we'll try to improve on this bound given by alteration method. Okay. Okay. So motivation. In order to motivate, let us first begin with the following definitions. Okay. Suppose so the first definition is that of a K-uniform hypergraph. So a K-uniform hypergraph is a graph with vertex set V and edge set E. So put emphasis on this edge set E, because this edge set is no longer, so elements of the edge set no longer look like this. So suppose we have our bona fide simple undirected graph, then our edge set is nothing but just an unordered pair of vertices, right? So in hypergraph, what we essentially have is, so in K-uniform hypergraph, what we essentially have is a K-tuple of vertices. Every edge is a K-tuple of vertices. Okay. So what happens now is that suppose how do we visualize this then? So the graphs that we deal with, those are essentially two uniform hypergraphs. Okay. It's clear from the definition. So how do you visualize three uniform hypergraphs? We can visualize them in terms of Venn diagrams as simply as this. Suppose we have 6 vertices, then we can use Venn diagrams to, I mean, I should draw the vertices somewhere else. Maybe here. So every Venn diagram is an edge set. Okay. So, and all right, so this is the setup for K-uniform hypergraphs. And the degree of a vertex is said to be the number of edge sets that it belongs to. Okay, that is how we define degree. So what is two colorability? So it is our an extension of our notion of two colorability. So suppose we have this path of length 1. Okay, then we know that this is two colorable because there does not, if we color, I mean, there exists a coloring with red and blue colors such that no edge in this graph is monochromatic, right? So that is that is what we mean by two colorability of our graph. So what happens to two colorability when we have 3 vertices? So it is no longer two colorable, because if you start with red and if you ensure that this has a different color, and since you have run out of colors, you have to put one of the same colors back here. So that ends up giving you a monochromatic edge. So so a two coloring of a hypergraph is a mapping from the vertex set of the hypergraph to a binary set of colors, red and blue, such that no edge is monochromatic. Okay. And a hypergraph G is said to be two colorable if such a coloring exists. Okay. So suppose we color the edges of a hypergraph G uniformly at random, independently of each other. Then under what conditions can we guarantee the existence of a coloring assignment such that there are no monochromatic edges in G. Okay, so we will. So this is the question that we are asking now. That suppose we have an. Oh, I'm sorry. I guess so. This should be vertices and not edges. Okay. Okay. So yeah. So now we want to ask ourselves that if we color with using two colors, then under what conditions can we guarantee that there exists a coloring for which there are no monochromatic edges in the hypergraph? Okay. So I'll come back to this. That this is a. I'll show you that this is a sufficient condition for the two coloring to exist. So, okay. So here's a framework that we are going to work with for introducing the Lovász Local Lemma, which is our main result. So suppose we have n bad events. Okay. E1 to En. What are bad events? Bad events are events that we want to avoid. So ideally, we would like probability EI to be 0. Okay. So in the context of graph coloring, what can be bad events? Bad events may be the presence of a monochromatic edge in the graph. Okay. So we want to avoid such kind of events, right? So what we want to do is we want to ensure such a thing, that the intersection of EI complement, that none of the bad events occur, that has positive probability. Okay. So what are some sufficient conditions under which we shall be able to ensure this? One of the sufficient conditions is this, right? Why? Because this follows from this fact. This is greater than right? So if the sum of probabilities of the event is strictly less than 1, then we shall be able to ensure that this is greater than 0. Okay, but notice that this will not hold, right? I mean, this is not a probability unless the events are disjoint. So there is every chance that this summation will be much larger than 1. Okay, so I mean, we have so this is one sufficient condition. Fine. What is the second sufficient condition? That these bad events are independent of each other. Okay. So if such a thing happens, then what we can write down, I mean, under the assumption of independence, we can write down that this is just so if such events have a probability of if they are not sure events, none of them are sure events, then we can ensure that this is greater than 0. Okay, so we have managed to avoid, I mean, at least existentially, we have managed to find an omega in the sample space, obviously, such that omega belongs to, okay, if such a condition holds, if these two, either of this or this sufficient conditions hold. But these sufficient conditions are rarely met in practice. Okay. So we try to see whether, so one, consider one extreme case where these events are disjoint and E1 to En, the union of that is the entire sample space, right? So then this inequality will then become an equality, and then this value will be 1 because union of EI is in that case the entire sample space. So this probability will become 0. So disjoint events are dependent. So under a case where we are considering disjoint events and they span the entire sample space, we cannot ensure that probability of intersection EI complement. So that is essentially empty, right? So we will have to settle somewhere between complete dependence and complete independence. So let us try to introduce dependence into, a dependent structure into these events E1 to En and see what happens. Okay. So before going to that, we'll just come back to this coloring problem. So in this coloring problem, what happens is that, so we define the events, our bad events, to be that the edge I in this graph is monochromatic. So we don't want that, right? If a two coloring exists, then we surely don't want this. So this is a bad event in this case. And we want to ensure that such a probability should be greater than 0 at all costs. So from this union bound, the sufficient condition that I gave you just now, we need to check whether this value is greater than 1 or less than 1 to verify that sufficient condition, right? In such a case, what we see that, so what is probability of here? What is the probability that an edge is monochromatic? So your an edge is nothing but k many vertices, right? So you have two, there are k many vertices. So you have two ways of independently coloring all these vertices. So the total number of ways that you can color in is 2 power k, and this will be monochromatic if all the vertices are colored red or all the vertices are colored blue. So this probability is nothing but, once we sum this up, this is nothing but 1 by 2 power k minus 1, right? Okay, now, so a sufficient condition would be this, because in that case, this sum will fall below 1. But essentially, hypergraphs are used in modeling large social networks, right? So you have a large social groups with lots of people in it, and you check intersection with other social groups. Okay, so in general, it's a very large graph, and you cannot ensure that the number of social networks in this graph will be low. Okay, there will be a lot of social networks that interact. So, all right, fine. So we cannot ensure that such a condition holds. So a very bad thing to say would be that we cannot even ensure in such a case, right? From if we have such a sufficient condition, then if we just add 1 to this, even then our argument fails. So we need better sufficient conditions now. Okay. So now we have come to the topic that we wanted to talk about. It is the symmetric Lovász Local Lemma. So before going ahead, we shall need the notion of mutual independence, which we will make precise with the following definition. So let A0, A1, .an belonging to some sample space denote events. So A0 is said to be mutually independent of A1 to An if A0 is independent of every event of the form intersection of Bi, where Bi are events of the form Ai or A complement. So here, this is nothing very fancy. I'm just highlighting the difference between pairwise and mutual independence here, because going ahead, we'll introduce that, the dependent structure that we're introducing, that will be restricted, and outside that, outside the set of, for a fixed event, outside the set of events that fall within the dependent structure of that fixed event, we want mutual independence with the remaining events. Okay, we don't want pairwise independence there. So very trivial example for, there are B1s also who are attending this conference. So trivial example for why pairwise independence does not imply mutual independence is that suppose three friends are tossing a coin independently, and suppose they are essentially equating their outcomes. So suppose their point toss outcomes are some A1, A2, and A3. So A1 denotes head or tail, A2 denotes head or tail, A3 denotes head or tail. So if you're just comparing the pairs of outcomes, so such events are pairwise independent of each other. So the event that A1 is equal to A2 is independent of A2 is of A3, and for all the three possible pairs. But mutual independence does not hold, because once you know the two pairs, once you have the so knowing the two events together determines the third event. Okay, So that violates the notion of mutual independence. Okay, so we need a stronger thing than pairwise independence here. So and also it will be helpful to keep a graph in mind. Okay, so a graph of, say, suppose you have 5 events. So you denote, so you have E1 to E5 corresponding to this EI, the indices. You consider a graph. Okay, say one of 5 vertices. 2, 3, 4, 5. And for the events that are dependent, suppose E1, E2 are dependent and E3, E4 are dependent. Okay. Maybe E2, E3 are also dependent. So for each such dependence, we'll denote an edge between the 2 corresponding index vertices on this graph. And we will ensure that the set of vertices with which, in this case, it is just 5. So maybe I'll just add another event to highlight again this pairwise independence and mutual independence concept, that with which this does not have any edge. It does not have any edge with this as well and this as well. So with these 4 events, it is mutually independent. Okay. So going ahead.
By the way, you are almost out of time. Okay. It's about 30 minutes.
Okay, so just 5 more minutes maybe.
Okay, you and Soham.
5-7 more minutes. Yeah, I think Soham has to speak also. Yeah, after this Soham will speak. So what is the allotted time? I mean, we were supposed to end at 11:30, but did we start off a little late?
You started at 11 and it's currently 11:33. Okay. So I thought it's 30 plus 30. Each of you is going to take 30 minutes is what I thought.
Okay. Actually, it was 15 plus 15. So I'm already way out of time.
How much is Soham?
But yeah, after this, Soham has a presentation. I'll just make it very brief then. So
okay.
All right. So the lemma is that, so suppose you have these n many bad events, and all of the bad events are bounded by some probability p. So there is at most a chance of p that these events occur. And suppose each bad event is mutually independent of a set of all other bad events except for at most d many. So ei is dependent on less than equal to d many each's. Okay, so that is for each i. Okay. So if such a condition holds, then there is a positive probability that none of the ei's occur. That intersection of ei complement is ensured to be 0 if e times p times d plus 1 is less than equal to 1. So this is our known constant e. This is the upper bound on the probabilities of the bad events. This is the number of dependencies of each event. I mean, the upper bound on the number of dependencies on each event. So essentially, rearranging this, we can say that if d, or the number of dependencies, is at most this, then we can ensure, or then this is a sufficient condition that none of the events occur with positive probability. Okay, so going back to our hypergraph example, okay, I think, yeah. So going back to the two colorability problem, we can now make the following claim that a K-uniform hypergraph is two colorable if every, so what is dependency in context of vertex coloring of a K-uniform hypergraph? So the coloring configuration will of two edges will be dependent on each other if and only if they contain at least one vertex in this intersection. Okay, so essentially dependency is equivalent to intersection between edges. Okay, so using the Lovász Local Lemma, we can now say that so here we have E, and we derived that the probability was 2 per k minus 1, and it is d plus 1. So rearranging the terms gives us d is at most this. So now notice the very interesting thing that is happening. here in this sufficient condition, we had a dependence on the cardinality of the edge set, right? But using this lemma, so while stating the lemma, you might have made the observation that the conditions of the lemma is independent of the number of events. That justifies the name local. Okay. So here also, in the final sufficient condition we are deriving, there is no restraint on the number of edges in the hypergraph. Okay. So this is a very beautiful result. And we can also have the following corollary that for every k greater than or equal to 9, every k uniform k regular hypergraph is 2 colorable. Okay, so essentially the number of dependencies is in that case is less than or equal to k minus 1. So if you put this here and then you try to find the first value of k for which this falls below 1, that value of k turns out to be 9. So but this is a little outdated because I think for k greater than or equal to 4 it has been shown. So okay, so using the local Lovász lemma, we can improve the alteration method bound that we had obtained earlier. And this was obtained by Joel Spencer in 1977. So way back in 1977, and this is the best known bound on Rk, k till date. I mean, there has been no improvement in the last 45 years or so. So, okay, it's a very simple application of the local Lovász lemma. All we need to do, we calculated the problem. So what is a bad event here? The bad event here is that complete graph kk is monochromatic. Okay, so how many intersections can be there between two complete graphs? I mean, the coloring, the edge coloring of two complete graphs, the configuration of the two edge colorings will be dependent if there are at least two vertices in this intersection, right? So how can we count? We can essentially then count by so how many complete graph kk? So for a fixed kk, say kk1, so how many complete graphs intersect kk1 such that the coordinate, I mean intersection in terms of the vertices, such that the cardinality of the intersection is greater than or equal to 2. So that can be done in k choose 2 into n minus. So you choose two vertices from the complete graph kk1, and you choose k minus 2 vertices from the remaining, and then you obtain the number of dependencies is this. So find the maximum value of n that satisfies this inequality. Then you see that the bound that is obtained is this, which improves A dash's bound by a factor of 2. And this is the base one. So, okay, the last thing, I had actually included a lot of things after this, but I don't think I'll have time to present. So the last thing that I'll state a more general version of the local lemma. So it is a stronger version, mind it, than what we have due to the symmetric. So this is the asymmetric version of the local lemma, where I'm removing the restriction that all the probabilities are bounded by the same quantity. So there might be a probability which is very small. So why would I use the same bigger upper bound for that? So if we can bound, so let me state the asymmetric Lovász local lemma. So essentially, due to dependence, what happens is that suppose we had no dependent structure in U1 to U1, then essentially what we would have is this term would not appear. Okay, so this is due to the event EI, and this part is due to this sort of a penalty that we are paying for the introduced dependent structure. Okay, so I'll make this clear once I state the theorem. So E1 to En are events, and let this, so I've named this Ni in consistency with this idea. I drew a graph here, right? So this graph, this dependency graph that I drew here. So Ni means if you pick a vertex here, or maybe vertex 2 here, then the set of neighbors of 2 is essentially the set Ni. Okay. So EI is mutually independent of all Ej that are not in the vertex set, neighbor set, and not obviously including that own vertex. Fine. So if we are able to find real numbers in closed zero open one, for which the probability of each EI is less than or equal to this quantity, then we can ensure that intersection EI complement is greater than or equal to this probability. And since these are strictly less than 1, this would be greater than 0. Fair enough? But as you can see, it's very difficult to actually find these numbers. Okay. So, I mean, so in general applications, it's very difficult to apply this lemma. So, but why did I state this lemma? Because actually, I wanted to show that the symmetric Lovász local lemma that we described earlier, that follows as a direct consequence of the asymmetric local lemma. So if we set each xi here and xj also, I mean all x1 to xn here to be 1 by d plus 1, then let us see what happens. What essentially happens is, so I have for a given I, this is just xi into probability j belongs to the neighborhood of I, 1 minus xj. So essentially I'm considering, so crucially remember that this xi is a dependent, I mean, these are in some sense functions of the events, okay, if I'm allowed to say so. Then okay, then this is setting xi equal to 1 by d plus 1. So we will see what is the motivation behind setting xi to be such a value. This is essentially 1 minus 1 by d plus 1. So degree of I will appear here, right? So the number of terms in this product is precisely the degree. So we know that degree of I is less than or equal to d because each I is dependent on at most d many events. Okay. So we can write, since this quantity is less than 1, we can write that this holds. Okay. Right? Again, I can, so from here I can write down it's greater than or equal to 1 by d plus 1, 1 minus whole power d plus 1, right? And we know that from the famous inequality that this is greater than 1 by. So that is how this exponent appears here, and that's what justifies setting this value to be this. It gives us back our Lovász lemma conditions. So if the conditions of the Lovász local lemma are satisfied, if EPD is less than or equal to d plus 1 is less than or equal to 1, then 1 by d plus 1 times 1 by E, that is greater than or equal to P, which is precisely, which is again in turn greater than or equal to this. So for xi equal to 1 by d plus 1 for all I, we are able to satisfy the conditions of the asymmetric Lovász lemma. And using the assumptions of the symmetric Lovász lemma, we are able to establish directly the conclusion of the symmetric lemma. Okay, so I thought that I would go into more details, but I think I've run out of time. So for people who are interested in reading out further, I have given some advancements, I mean, beyond LLL, its variants and stronger versions in the presentation. But I guess, and okay, so I guess this will be it because I've run out of time. Now I'll hand over the presentation duties to Soham. Thank you so much.
Thank you. Soutim, sorry, Soham, can you now, I've made the co-host this laptop also, previous laptop. So. And yes, since this went about 3 times the expected time,
I'm so sorry, sir.
So
this is totally unplanned.
Soham, you have to well, be brief. Yes. Try to be 15 minutes as you heard now. Okay. Great, thanks. Go ahead.
Hello.
Yeah,
good morning, everyone. Okay, so I will be continuing what Soutim had just started, the Lovász Local Lemma, and I will be giving special emphasis on its several usage and applications. So let's see. So this is a very brief outline of what I'm going to present. So first of all, I will be dealing with a very basic problem which arises in computer science and propositional logic, which is the Kcnf problem. And I will show that how it's similar to the hypergraph coloring problem as Soutim has presented in terms of the LLL. So now, so far, what we have done is that we have seen LLL as a non-constructive method. So as to say, it does not give us a point in the sample space which avoids all these bad events. However, we have a very strong algorithm, which is the Mozart-Tardosh algorithm, which essentially gives us a point which avoids all these bad events. It's a very simple algorithm, and yet it is very efficient. So we will discuss that. We'll discuss something about the proof of correctness. We won't go into the details because I believe I don't have too much time. We'll discuss something about parallelism, and then we have something on packet routing as further applications of the LLL. So let's see, let's start. Okay, so what is the Kcnf? Cnf essentially stands for conjunctive normal form. And what is the Kcnf? Suppose we have Boolean variables, x1, x2, xn. So taking values in 0 and 1. And we have a clause is of this form, say x1. So they are joined by disjunction operator, and say not x4. And we have some such things. So if there are k elements in clause, then we call it a C clause. So what a Kcnf is that it is a conjunction of such C clauses. All right. So we have m such clauses, and they are connected by this conjunctive operator. And the final Boolean expression that we get, phi, that is called a Kcnf. So the question is whether there is an allocation of these variables, Boolean variables, such that this phi is satisfiable. Satisfiable in the sense that this evaluates to 1. So let's see. For phi to be satisfiable, all the Ci's must be 1, right? All the Ci's must be satisfied. So this is what we observe. And suppose, how do we formulate this using the LLL? So suppose we randomly assign values to these xi's with uniform probability. So xi takes values 0 and 1 with probability half and half. Now what happens? What is the probability that a particular clause Ci is violated? A Ci is violated when all of the literals in that expression are 0, right? Since they're joined by disjunction. So that probability would essentially be 1 by 2 to the power k. So essentially, this is what the probability is. And so suppose we have less than 2 power k minus 1 clauses, then what we can show is that using the union bound, that we can avoid all such bad events. So what is this bad event? So Ci is violated. If I call this event as my bad event Ei, so probability of Ei is 1 by 2 to the power k, and union of Ei, and union of Ei would be less than this sum, right? As Soutim has mentioned, the union bound. If I have less than 2 to the power k minus 1 clauses, this would be simply less than 2 to the power 1 minus k into 2 to the power k, which is half, equal to half. This is less than 1. And so we can claim that there exists such a omega for which all the bad events are avoided. However, we have a stronger version, namely, if any xi appears in at most 2 to the power k by ek many clauses, then also this result holds, that we can find such an omega. So this follows from LLL. So let's see. So if each xi appears in at most 2 to the power k by ek clauses, so a clause Ci would be dependent on at most 2 to the power k by ek into k many clauses, which is 2 to the power k by e. Once we have this will be my dependency number. Dependency number will be actually less than this. So we can calculate our EPD, so as to say, as was shown in the symmetric version of the Lovász Local Lemma. This would be simply this, right? Our P is found to be 1 by 2 to the power k, and this comes out to be 1. So using, I guess Soutim did not find the time to state this, that if even if EPD is less than equal to 1, the Lovász local lemma holds. So this is very similar to the hypergraph problem, the Kcnf one, but this will serve us a motivation for the theoretical background that we will lay to discuss the Mozart-Tardos theorem. So what is that? So let's see. So essentially, if we come back, so each of these clauses, let me use a different pen. So each of these clauses is only dependent on some variables, right? Some Boolean variables. So that is what will serve us as the motivation. So this was the result that I just proved. If each xi occurs in at most this many clauses, then phi is satisfiable. Okay. So we'll lay down this theoretical setup. So given this xi is independent and the bad events E1 to EM, if each EI can be completely determined by a subset of these variables, as was in the Kcnf example, then we have a very strong algorithm. Let's see. So how would the dependency graph of this look like? So dependency graph consists of these events as my vertices. So if I were to draw that, E1, E2, E3, and so on, these are my vertices. And I join E1 and E2 only if they have some variable in common. So that is essentially my dependency graph. And let's see what the Mozart-Tardos algorithm says. So it's a very simple idea. So since I can express or completely determine EI using a set, what is that set? I call that variable EI, some set consisting of the random variables. So I will sample each of the xi's in this variable EI. So say this set is xi1 to xij. So I will start sampling. Initially, I have x1 to xn, and I have some probability distribution defined on that. I will sample. I start sampling. I check if EIs are satisfied. E1 to EM are satisfied. I don't want them to be satisfied, right? They're bad events. I want to avoid them. So if something is satisfied, I don't want that. So suppose E1 is satisfied. So what I do is that I resample this event. I resample the variables that completely determine this event. So I resample that. Due to this, what happens is that some other event is violated, or rather some other event EI is satisfied. So again, I have to resample and this process continues. So this is what essentially the Mozart-Tardos algorithm is. So let's see, I have written it down here. So for every X belong to this chi is just X1 to Xn, we first sample using the distribution. And if there are violated events, meaning if EIs are satisfied, so we pick a violated event arbitrarily, and then we sample. We again sample such that it's satisfied, such that EI does not occur. So we sample and we go on till there are no more violated events. And finally we return the assignment of the exercise for which none of the EIs occur. So a priori, if we see this algorithm, it is not immediately clear why this should at all converge. Because if a particular event, say EI and EJ, have variables in common, then suppose at first EI was satisfied by some allocation and we resample it, then that would cause a change in the values or evaluation of EJ, right? So this might again be violated. So it is not very clear that this algorithm would actually converge. But what Mozart proved in 2008 was that this is essentially a very efficient algorithm. And Mozart and Tardos together in 2009 essentially improved upon that. So let's see the very beautiful result that we have here. So this was proved by Mozart. So the expected number of resamplings that we would need is less than this expression. What are my XEIs here? The XEIs are simply the things occurring in the asymmetric version of the Lovász local lemma. So we did not get much time for that. So I'll just write it down so that just a minute. So this was essentially some product into 1 minus x ej, where my ej belongs to the neighborhood of ei in the dependency graph. So this xei's occur here in this resampling step. So you see that this is nothing but a constant. Given the XCI, this is nothing but a constant. So this is essentially a ON sort of algorithm. It's very efficient, right? So depending on the number of variables, this is a ON sort of algorithm. So proving this is not at all simple. We would need, there is a very beautiful argument that Mozart essentially presented in his paper. And I will essentially highlight the main details of the algorithm and ideas of the algorithm. So this will be in 5 steps. So let us see what they are. So first we will define what is called the log of execution C. So what is a log? A log is simply like the logbook. Okay, so what Mozart-Tordos algorithm does, it continuously resamples, right? So say we assume discrete time points. So at the first step, it resamples, say, event C1, and then it resamples event C2, and it goes on CT. So this is essentially my logbook, which I denote by C, the log of execution. So what I am to show is that the expected length of this logbook is this, less than equal to this. So for that, we'll construct a particular tree, which is called the witness tree. Why do we need to construct a tree? Because this tree has certain properties, which will essentially give us our proper bounds. We'll study the properties and let's see what they're. So I'll just briefly describe how we can construct such a witness tree. So the witness tree at time point t begins with the root CT. CT is essentially the event that was resampled at time point t. Okay, so we begin with CT. This is my vertex, and we look at CT minus 1, the event that was resampled at time t minus 1. We look at that, and if CT minus 1 belongs to the extended neighborhood of CT, so extended neighborhood meaning that in neighborhood including itself. So E belongs to the extended neighborhood of, say, some event F, if E belongs to this set, simply. So this is the neighborhood of F, and this is F itself. So E can be either F or it may belong to the neighborhood of F. So that is the extended neighborhood. So if CT minus 1 belongs to this extended neighborhood, then what we do is that we draw an edge. We include it in the graph. If it does not, then we simply skip CT minus 1. Okay. So suppose it does belong and we have included it. So let's see how the next step proceeds. We look at CT minus 2. And we look at all those vertices which are in the extended neighborhood of CT minus 2. Here we have just 2 vertices now, these 2. So we look at those and suppose both of them are there. So we join it to the one which is at the greatest distance from CT. So CT minus 1 is the greatest distance from CT. So we join it here. If CT minus 1 did not belong to the extended neighborhood of CT minus 2, then we would simply join it over here, right? So at step I, what we are essentially doing is that we are checking all the vertices that have been included before, whether they are in the neighborhood, extended neighborhood, and we join it to the one which is at the greatest depth from CT. So that is what we are essentially doing. And we obtain a tree of this kind, which would essentially terminate when we have C1. And this entire tree is what I call my witness tree at time t. Okay, so this witness tree has certain properties. One property is very clear. So suppose we at time points R and S, suppose R less than S, what can we conclude about CR and CS? So if R less than S, then we know that CS was included before CR, right? Because we are first including T, then T minus 1 and so on. So CS already exists in the graph. Now suppose CR and CS have some variables in common. If they don't have any variables in common, then we won't include CR. But if they have variables in common, then we can either attach CR as a child of CS, or we can attach it to a node that is at a greater depth than CS, because that's what this W tree construction demands, that we attach it to the node which is at the greatest depth, right? So what I am claiming, or what is immediate, is that CR is at the greater depth than CS, and this is a strict inequality. Having shown this, it is very clear that all the nodes that are present in a particular level are independent. Because if they were dependent, or if they overlap, then this relation would hold, right? This relation would hold. So they must be independent. So here I have listed down those properties, that what I have just said, that if R less than S, then the depth of AR will be greater than the depth of AS, and all the vertices at the same level are independent. So we have a non-trivial result, which is this, that all trees up to time t are different. So this is not very difficult to see. So what are you doing? So suppose at some point they're equal. Just 1 minute. So suppose at time t and s they're equal, and suppose t less than s. Okay. So this CT was formed. Let us try to see what CT is. So this witness tree at time point t, let us count how many of the vertices in this witness tree are exactly equal to CT itself. Okay. So we call the cardinality of that as n. So there are n many vertices in the witness tree T which are exactly equal to CT. Now CS has at least n plus 1 many such vertices. That is what I am saying. And this is clear because at time point S, I have again included the same value. Right. So essentially the set of vertices of these two, of witness tree T and witness tree S, are not same, and so they're different. So at different time points we'll get different witness trees, and this will help us to prove what we want to show. So we have something called the probability of occurrence of a witness tree. So what does that mean? So a witness tree occurs. That means that at some point, so suppose I have a tree T. T occurs. What does T occurs mean? That at some point T, W tree, the witness tree at time point T, is exactly equal to T. So then we say that T has occurred. Okay. So what we can show is that the probability of occurrence of the witness tree is this. What is this? This is nothing but this expression. So suppose let us draw a witness tree with events, say P, and see what this is, T and E. So let's move from bottom up. So what is the probability that E is satisfied? E satisfied meaning that that clause is violated in the Kcnf problem, if you assume. So that is essentially probability E. And the Mozart-Ardos algorithm essentially resamples independently after each iteration. So here the variables resampling is independent of the resampling here. So it goes on resampling. So what I have is that for this E to be true, the probability is E, and then for E and D to be simultaneously true, the probability is simply this, because they're independently sampled, and so on up to A. Right. So essentially, this is what this expression says, that I multiply the probabilities of all the events that are in the witness tree, and this would be the probability that the witness tree occurs in C. So this is a very simple argument, but I won't go into the details of that. This essentially proceeds by fixing a seed. So essentially, you can think of that every pseudo random number generator begins with some seed, and if they both begin with the same seed, then essentially the same set of values are obtained for this sort of occurrence. And the result follows from here. So let's see what are the implications of this result. So I have written it down. So what is REI? Let me just make it small. REI, REI is essentially the number of resamplings of the event EI. So when I'm going through with the Mozart-Ardos algorithm, I look at the number of times EI has to be resampled. Okay. So to explain, number of times EI needs to be resampled is essentially equal to the number of times EI occurs in the logbook, right? Because all the witness trees are different. So number of times EI occurs is essentially the number of times EI has to be resampled. And the number of times EI occurs in the logbook is essentially this. That actually this particular witness tree occurs in C, and I sum up over all possible witness trees starting from EI. That is my set, this one. So I have this expression. Once I have this is fairly easy. We take the expectation on both sides. So this becomes the probability, and we have an expression for this probability. So I have this. And using the asymmetric version of the Lovász Local Lemma, what do I know? I know that probability EJ is simply this expression, right? So this is using the asymmetric version of the Lovász Local Lemma. So I have this expression, but I did not want this, right? I wanted this expectation of REI to be bounded by something of this form, XCI by 1 minus XCI. So where does this come? So this comes by recognizing this expression as something relating to a branching process. So this essentially, this expression also comes in when we construct a tree based on a branching process scheme. And from there, the upper bound has been proven. So I don't have the time to go into branching processes. So I will just state it very briefly. So what do we do? So essentially, we start with some vertex E. This is my set. And how do we come across its children? So we look at all the vertices which are in the adjacent neighborhood of E. The extended neighborhood of E. Suppose some event F is in the extended neighborhood of E. So we include F as a child of E like this with probability XF. And do not include it with probability 1 minus XF. So that is how we create something called the witness tree, Galton-Watson branching process tree. And using this, we can show this result, that the probability that the witness tree Galton-Watson is equal to the witness tree is this big complicated expression. This. So this is a very well established result. And why does this come up is that this expression comes up. This expression. We recognize it as that expression, the same expression that came up in the while we were trying to prove this expectation REI, this expression comes up. So essentially, what do we have? From here and doing some algebra, we can show that my number of resamplings of the event EI will be less than equal to 1 minus XEI. I'm sorry, this would be in the. So I just cross multiply here and get this expression. Times probability that the witness tree Galton-Watson is equal to my witness tree. Now the bound seems achievable, right? So essentially, expected total number of samplings would be just sum of all possible events that needs to be resampled. This would be a sum, and this would eventually be bounded. Not eventually, this can be bounded by this expression. So that is how we obtain this bound. Okay. So I cannot go into details of the branching process. So I'll discuss what is parallelism. So what we are doing in the Mozart-Ardos algorithm. So we were picking just one violated event at a time, right? Instead of that, we can greedily pick a maximal independent set of violated events. What is a maximal independent set? It's all those events of the type which do not have variables in common, right? So changing the allocation of variables for one such event does not affect the other one. So at one step of the Mozart-Tardos algorithm, we can do such things. We can pick all those a maximal independent set of violated events and resample them independently. So why is this important? This is important because if the LLL conditions were only a bit weakened, what do I mean by bit weakened? That, So what do I know that? So let's recall what our asymmetric form of the Lovász Local Lemma was. So instead of xei times some product 1 minus xej, I'm not writing the entire thing here. We have 1 minus epsilon times this. So this is a weakened version, considering that this has some epsilon. So this gives a stricter bound. So considering this, but if we have this, then we can actually show that using parallelism, we can have a logarithmic bound for the expected number of resamplings. This is a logarithmic bound. So instead of summation this, we have log of summation this. So this is what can be shown. And this is where we come to the end of the Mozart-Tardos algorithm. So I will just discuss one more application of the LLL that has been used in packet scheduling, which essentially uses the Mozart-Tardos to find the suitable omega. So what is packet scheduling in networks? This is quite a modern application and a lot of work has been done. So we have certain things called packets. Packets are just, you can think of as information. We have a certain graph and so the graph associated with the graph are some packets. So there is a starting node and the packet must move through some path in the graph and reach a destination node. So for each such packet, a path is specified. So it must move through that path. Now the catch is that through each edge of the path, only one packet can flow at a particular time point. So you can see that if multiple paths intersect like this, then there can be something called some sort of a congestion here. If multiple packets arrive at a particular junction, then they must wait, right? Depending on how many packets have arrived, then they must wait because the outflow is just one. So we want to design a packet scheduling policy. What does this means is that we want to state which packet flows through which edge at which time point, such that the total time of flow is minimized, such that all the packets reach their destination. And we want to design a policy to minimize this time. To that effect, we will define certain things. So something called the congestion. So this is the maximum number of paths that share a directed edge. Obviously, if many packets come together at a particular time point, then they must wait, right? So the time would increase, the time required to send out those packets to their destination, that would increase. So that's why this is relevant. And we have something called the dilation, which is the maximum path length that occurs in the path system. So essentially it is the maximum among this. So if a particular packet has to travel a longer path, then obviously the time would increase, right? So using these two parameters, we have a very simple bound. So what is this bound? So the time required is greater than or equal to this maximum. So this is immediately clear, right? Because T obviously has to be greater than or equal to D, because one packet has to travel the path, such a path of maximum length, and this has to be greater than or equal to T. It also has to be greater than or equal to C, because if they are congested at a certain point, so if the maximum number of paths, also C is the maximum number of paths that share a directed edge. So if all the packets arrive there, then they have to wait at least C time points, right? So that is why T has to be greater than or equal to this maximum number. And what important result we have is that this trivial lower bound can actually be achieved up to a constant factor. So this is essentially the result due to Leighton, Max, and Richa, that in this above model, there is always a packet schedule that achieves OC plus D delivery time. So C plus D is very much comparable to, because this is less than equal to 2 times maximum of CD. So this, in this linear time, this delivery, this allocation is possible. So this is essentially, and they have proved this using some advanced version of the Lovász Local Lemma. So if someone is interested, one can easily see this. Okay, so essentially that's it. I'm done with my presentation. So this is all there is. Thank you very much.
Thank you, Soham. Yeah, are there any questions? Okay, I guess if there aren't any, then let's thank both the speakers again for nice joint talk about the Lovász Local Lemma and further follow-ups.
Yeah.